Hey guys, welcome to video 59. Today we're going to talk about power supplies for vacuum tube based amplifiers, which are typically guitar amplifiers. We're going to start out by looking at power supplies that use solid state diodes for rectifiers, and we'll work our way up to vacuum tube based rectifiers. Okay, now the schematic we've got in front of us right now is pretty typical of the basic tube amplifier power supply. Let's start by looking at the transformer. Alright, this is a Hammond 269GX. The high voltage secondary is rated for 450 volts RMS with a center tap, and it can supply up to 75 milliamps to the load. The low voltage secondary, 6.3 volts RMS, is to power the heaters of our tubes in the amplifier. We're not going to worry too much about that section today. Now, the secondary is rated in volts RMS, so we want to know what the peak voltage is, so we'll multiply 450 times the square root of 2, and that gives us 636 volts peak across the entire secondary from red lead to red lead. But we're typically using a 2-diode full wave rectifier, and that means that we're effectively cutting our secondary voltage in half to 318 volts peak. So neglecting losses across the diodes or the resistive losses in the secondary winding, this means we're going to have about 318 volts present at this node that feeds into our filter. Now let's talk about our diodes here for a second. I've specified 1N4007s in this particular circuit, and these diodes are rated for a peak inverse voltage of 1000 volts. They can carry a forward current of 1 amp, and they have a maximum forward surge current rating of 30 amps. That means that these diodes can carry up to 30 amps of forward current, but it has to be limited to a time less than 8.3 milliseconds. That's half of one cycle of the 60 Hertz AC line. Now, in this circuit, our diodes have to be able to withstand a reverse bias of at least 636 volts. A 1000 volt breakdown is sufficient to give us a pretty good safety margin here, so we're good. Now, as far as forward current goes, again, the 1N4007s are good for 1 amp, but if we were going to be drawing much more current, we might want to switch to the 1N5408s. They're also 1000 volt reverse breakdown, but they're rated for 3 amps forward current and a forward surge current of 180 amps. Now let's go on over to the primary side here for a second and talk about what we've got going on. We're using a single pole, single throw switch here to control power, and we always want to have that switch connected to the hot line of the AC mains. It's also a good idea to use a fuse or a circuit breaker. Typically 1 amp is sufficient, although sometimes we may need to go up to 2 amps here as well. Okay, let's go on over to the output side of our power supply here, and let's talk about our filter. What we've got is an RC pi filter, and it's also what's known as a capacitor input filter. Alright, it's obviously an RC filter because that's all we're using, resistors and capacitors. It's a pi filter because it kind of looks like the Greek letter pi, and we call it a capacitor input filter because the first reactive element that we see coming out of the rectifier is a capacitor. Now, the output terminal I'm labeling as plus VPP. That's to go along with our typical transistor notation of VCC for our supply rail. And since this is going to be connected to the plates of the tubes, I like to call it VPP, the plate supply voltage. In older equipment and data sheets, often this is referred to as the B plus rail or B plus line of the power supply. Now, coming back over to R1, R2, C1, and C2, Let's start with R1. This is primarily a surge current limiting resistor. It prevents C1 from drawing too much current initially when we first turn on the power supply. Its value isn't super critical. It could be anything from maybe 50 ohms to several hundred ohms. In this case, I'm typically going to use about 100 ohms, and that'll limit the current to usually somewhere less than an amp or two. And remember, the diodes do have a decently high surge current rating, so again, this value is not critical, but usually 100 ohms works pretty well. And as far as R2 goes, again, 100 ohms is a pretty typical value for this resistor. We can use both of these resistors to reduce our output voltage. It depends on the load current we're going to be drawing. Typically, we'll know what the load current is. It could be anywhere from maybe 40 or 50 milliamps up to 500 milliamps or more, but usually we'll know what it is, and we can choose resistor values here to reduce this voltage to whatever we want out here if necessary. And remember, we'll also have to calculate the power dissipation of these resistors depending on how much voltage they're dropping and how much load current we're delivering to the amplifier. Okay, now let's talk about our capacitor values here for a minute. In most guitar amplifiers, if you look at the power supply, C1 and C2 tend to be relatively low value caps, sometimes as small as 10 microfarads. Generally speaking, the larger the capacitor values, the less ripple you're going to have on your supply rail, and the less likely your amplifier is to have hum on the output. Now, there are other causes of hum, but if I can eliminate it here by using larger capacitors, that's what I like to do. As long as R1 is limiting the surge current to a reasonable value, there's no upper limit on these two capacitors. Okay, now I'm going to paste in the values we're using for these components today. We're setting R1 and R2 to 100 ohms, and we're going to do some analysis using PSpice for 20 microfarads and 100 microfarads for the filter caps. Now, keep in mind that the optimal values for these resistors and filter caps is mainly going to depend on how much load current you're drawing from the power supply. For a low power amplifier, say like a 5-watt practice amp or something, the load current might be in the 50 or 60 milliamp range. And for a higher power amplifier, 20, 30 watts RMS, the load current is going to be several hundred milliamps. And of course, for these larger current values, we're going to need to use larger capacitors here in our filter to keep the ripple down to a reasonable level. Now, the last thing I want to mention here before we do some analysis is R3, which is called a bleeder resistor. It's not absolutely necessary to have one, but I like to include it, and typically it's around 100,000 ohms or so. The function of this resistor is to drain the charge off of these capacitors when we turn off power. That way, if you're poking around inside the amplifier, you don't have to worry about getting shocked, and it's just a good safety feature to include. Now, what we're going to do next is take a look at some PSpice analysis results for this circuit. In this first example, we're setting our filter caps both to 20 microfarads, R1 and R2 are both 100 ohms, and we're representing our amplifier with a 5,000 ohm load on the power supply. This would be pretty typical of a low power practice amp, something around 5 watts RMS, Class A biasing. And this gives us a supply rail voltage of about 280 volts. Our load current is about 56 milliamps. And if we look at the supply rail voltage waveform, we see we've got about 6 volts peak to peak of ripple here. Now, that seems like a lot, but it really might not be that bad. We're going to be using some additional downstream filtering from the power supply that's going to reduce this. And depending on the output topology of our amplifier, this may not be an issue there either. We'll come back to that in a second. But for now, let's go on over and take a look at our capacitor charging current. We're basically monitoring the current through our surge limiting resistor R1, and what we see here is we reach a peak current of a little over 1.6 amps. That's way below the maximum surge current for our diodes, so we're perfectly fine here. And I'd also like to mention that if we were to look closer at these pulses, we'd see that each of these lasts for 8.3 milliseconds, 1/2 of the AC line period. And that's what's used by the diode manufacturers to specify their surge current ratings for the diodes. All right, now let's come over and look at this ripple voltage waveform again for a second. If we happen to be using a single-ended Class A output stage on our amplifier, this is probably going to be too much ripple to live with. We'll hear this as 120 Hertz hum on the output. If we're using a push-pull output stage, they happen to be pretty insensitive to ripple, and this might be acceptable. But in either case, I really don't like having this much ripple, so what we can do to get rid of it is increase the size of our filter caps, and let's do that by changing them both to 100 microfarads. Everything else in our circuit stayed the same, and notice if we come down and look at our supply rail voltage waveform, the ripple is almost completely gone. Now, because we've increased the size of our filter caps, we have increased the initial surge current, but it's still well within the surge capabilities of our diodes, so everything looks good. Okay, now let's make some modifications to our power supply. In particular, what we want to do is change our filter from an RC filter to an LC filter. And in this particular example, we've got an LC pi filter, and this is still a capacitor input filter because the first reactive component we see outside of the rectifier is a capacitor. Now, replacing the resistor that was here with an inductor is going to increase the order of our filter from second order to third order. That's going to reduce the ripple voltage even further. And additionally, because the winding resistance of this inductor is probably relatively low compared to the original resistance we had, we're not going to have as much reduction in the output voltage as we would have had with a resistor in here. And in these applications, the inductor is usually referred to as a choke. Typical values we'd have for this inductor range from maybe 4 henries to as large as 30 henries. The Vox AC30, for example, uses a 30 Henry inductor in its power supply. So using an inductor increases the performance of our power supply, but the main trade-off is that inductors like this tend to be relatively expensive. Depending on the amount of current it's designed to carry, that's something we do have to consider. The larger the load current, the bigger the inductor is going to be. So large inductors tend to be relatively expensive. These could cost anywhere from maybe $10 to $30, $40 or more, depending on the size of the inductor. Okay, now let's take a look at some PSpice analysis results for this circuit. If we set our filter caps to 20 microfarads, R1 100 ohms, the inductor 4 henries, and we maintain the 5k ohm load equivalent for our amplifier, these are the results we come up with. We get a supply voltage of about 286 volts. Load current is about 57 milliamps again. And notice that we do get some pretty smooth fluctuation in the supply rail voltage initially, and it does level off to about 286 volts after about 0.6 seconds. Now notice also that even with 20 microfarad filter caps, the ripple voltage is extremely small when we add the inductor, and that's the advantage of the inductor. It allows us to use smaller filter caps. Whether that's a good trade-off or not depends on your budget and how heavy you want the amplifier to be or not be, but in any case we do get good performance from this filter. Now also notice that our maximum charging current or surge current into the filter is about 2.5 amps, and that's well within the surge capabilities of our diodes, so everything looks good. What we want to do next is take a look at the final filter variation we have here, and that's called the choke input filter. Notice that where R1 used to be, we now have an inductor, and this filter has the characteristic that the output voltage is approximately equal to the average of the input voltage rather than the peak. The capacitor input filters charge to the peak value. The choke input filter produces an output that's roughly equal to the average of the input. So again, using the same values we had previously, 20 microfarads for our filter caps, resistor equal to 100 ohms, the inductor 4 henries. If we do some P-spice analysis, these are the results we come up with. We end up with a supply rail value of about 200 volts. Our load current is about 40 milliamps. It's reduced because our voltage is reduced. And notice that initially our supply rail voltage climbs to about 350 volts, then it drops down to a steady state value of about 200. And you can see that we do have some ripple present here. If we look at our inductor current, that is the current drawn from our rectifier, it reaches a peak of maybe 620 milliamps or so, then it drops off and reaches a relatively low value of maybe 100 milliamps peak to peak. So again, our surge current is not much of an issue with this rectifier. It's well within the capabilities of just about any diode you're going to use. Now, we're not going to spend much time talking about the choke input filter. It's not used very often in audio amplifier applications. What we want to do next is go on and talk about vacuum tube rectifier power supplies. Okay, so what we have here is the schematic for a typical power supply that uses a vacuum tube dual diode rectifier. In this example, we're assuming our amplifier draws 200 milliamps from the power supply. We're using a RC type pi filter, and right now I have a 5U4GB specified, but we could use any of the 3 rectifier tubes that we've talked about so far. The difference is that they're going to have different voltage drops across them because of the different perviances of each of the tubes. So based on the transformer that we've selected here, we're going to have 390 volts peak across each half of the secondary, and if we use the 5U4GB for our example, we're drawing 200 milliamps. If we come down to the characteristic curves here, at 200 milliamps, the 5U4GB is going to drop approximately 40 volts. That means our output voltage is going to be roughly 390 minus 40, which is 350 volts into the filter. If we use the 5AR4, at 200 milliamps, it's got a much smaller voltage drop across the tube. It looks like it's going to be about maybe 17 volts or so, and that would give us a power supply rail voltage at this point of 390 minus 17, which would be 374 volts. And finally, if we used a 5Y3GT in this position with 200 milliamps, it's going to drop approximately 68 volts, which means that we would lose 68 volts across the tube, and our voltage applied to the filter would be about 322 volts. Now, all 3 of the tubes that we've looked at here have the same pin out, so they can be used interchangeably here. And let's go take a look at their data sheets, or at least some excerpts of the data sheets, to get an idea of what kind of parameters we're dealing with. So for the 5U4GB, again, we see that the filament requires 5 volts at 3 amps. The tube can withstand a reverse voltage of 1,550 volts, can carry a forward current of up to 1 amp, and has a surge current rating of 4.6 amps for 0.2 of a second. Now over here, General Electric gives us some typical values for power supplies using, first of all, a capacitor input filter, which is what we have up top. And typically you can get output voltages from 3 to 450 volts. Typical filter cap value is 40 microfarads. We can go larger because we've got the surge limiting resistor R1 in there. And the output voltage at the input of the filter typically can range from 290 to 460 volts. Now, these are just typical values. We don't have to stay within this range. We could go much lower and somewhat higher as well. They also give us the typical component values for a full wave rectifier with a choke input filter. We wouldn't be interested in that, but it is available here if we wanted to use that. Now let's go on down and look at the 5Y3 GT. Its filament requires 5 volts at 2 amps. It can withstand a reverse voltage of 1400 volts. It can carry a forward current of 440 milliamps, and it has a surge current of 2.5 amps. And they're giving the typical values for a full wave rectifier with either capacitor input filter or a choke input filter. And the typical capacitor they're specifying here is about 20 microfarads. All right, and finally, let's go down and look at the 5AR4. Its filament requires 5 volts. It's 1.9 amps. It's a little bit more efficient than the other tubes. It can withstand a peak inverse voltage of 1700 volts, can carry 825 milliamps, and has a surge current rating of 3.7 amps. And again, we've got the typical values associated with a full wave rectifier with a capacitor input filter. They're specifying, they don't even give us a capacitor value here. And they've also got the values for a choke input filter specifying a 10 Henry inductor. All right, let's go back up and look at our schematic again. We're going to wrap this video up in another minute or so, but just a couple of comments. If you decide to go with a vacuum tube based rectifier, the power supply is going to be much more expensive because you're going to need a larger transformer with more iron and copper, and the vacuum tube rectifier itself is going to be much more expensive than solid state diodes. The 1N4007 or equivalent diodes that we've looked at are probably 15 cents a piece, maybe a little bit more. The typical 5U4, 5AR4, 5Y3, they're going to be at least $15, possibly much more depending on the source you get them from. And the power supply using the vacuum tube rectifier is going to be much less efficient than the solid state equivalent. So really the only reason to use a vacuum tube based rectifier in your power supply is for nostalgic reasons, or if you just want to be old school and that's what you're going to go with. But in any case, this is the power supply design that I will use in upcoming videos if we decide to go with a vacuum tube rectifier. And that's it for today, and I will talk to you guys next time around.